Hello and welcome to our discussion of the relationship between groundwater thickness and the urban heat island effect. The urban heat island effect, or the UHIE, is caused by an abundance of artificial surfaces in an area. Surfaces such as asphalt and concrete absorb more incident radiation from the sun than natural surfaces, and thus heat the area around them further, increasing the temperature in that area. This is most often seen in urban areas like cities where there are a lot of artificial surfaces, hence the term urban heat island effect. As these surfaces are impervious, they will often prevent infiltration of rainwater and runoff to groundwater storages, preventing recharge, which we hypothesize will create a correlation between the strength of the urban heat island effect and the quantity of groundwater in an area. As such, our research question is, what is the relationship between the quantity of groundwater in an area and the strength of the urban heat island effect? For our study area, we chose to examine the 100 largest cities in the US, the goal being to reduce noise in the data through a very large sample size. For each city, we collected data on the quantity of groundwater and the strength of the urban heat island effect. To begin with, we first have to answer, how can we measure groundwater? We retrieve groundwater levels in an area from GRACE data, which only has a 300-kilometer spatial resolution. This means that we have only one data point for each city, just determined from its latitude and longitude, that quantifies the amount of groundwater beneath it. That data was downloaded through the NASA PODAC drive, with the latest data sets being used corresponding to August of 2022. Our data processing was generally on the order of, first we would download the data from the NASA drive, then we would use Python and open the dataset with the netcdf4 modules, which are Python libraries. We can then extract the land water thickness measurements from the dataset and store, and in combination with a JSON file with all the information about cities, we can use the latitude and longitude measurements from that file to get the corresponding water thicknesses under each city. And we would then plot this against the corresponding urban heat island strength measurements on a scatter plot to see if there was any correlation. The GRACE data in general, for example, is really just one image. As you can see here, it corresponds to, for example, in this case, darker areas have more water and lighter areas have less water, and there's just numbers for each of the different points. Measuring the urban heat island, we decided to employ the techniques described by Wang Si et al., where we define the urban heat island effect as the difference between the average temperature of the urban areas of a city minus the average temperature of the surrounding suburbs. That is, as you can see here in equation 1 written a bit more formally. Our data flow was thus as follows. We would first retrieve the Landsat 8 imagery from the USGS machine-to-machine API. We then isolated the urban and suburban pixels in the image using the Artificial Surface Index, or ASI, as defined by Zhao Yonggan and Zhu Jiang. We normalized the ASI to correct for atmospheric distortion. We then set thresholds for that normalized ASI that help identify the urban and suburban pixels. And we then are able to compute the urban heat island effect, since we now know which pixels are urban and which pixels are suburban, so we can compute the average land surface temperature for each of those, as described in equation 1. As an example, for part of this process, consider the following image. This is the artificial surface index for the New York, New Jersey, and Pennsylvania regions, that is, the tri-state area in general. After filtering, we're able to obtain the following maps of the urban and suburban areas, which you can see here. Looking at a reference image of the population density of New Jersey obtained from the US Census, we can note how the identified urban areas align very well with the locations of New York City and Philadelphia. The suburban areas also line up quite well. They surround the urban centers and match the semi-populated regions of the reference map. After having measured the strength of the urban heat island and the groundwater level for every city, we went ahead and created the scatter plot of the data. Ultimately, we found that there was no significant correlation between the equivalent water thickness as measured by GRACE and the strength of the urban heat island effect. A linear fit of the data produces an R value of 0.14, indicating no correlation. As such, we have identified several reasons why no correlation was observed. I mean, of course, to begin with, it's possible that there just is no correlation in the first place. But if there was, we suspect that there are a few things that could have masked it. Firstly, the GRACE data is measured in equivalent water thickness, relative to a baseline, that does not depend only on water. That is, so that GRACE does not just measure the quantity of land in an area. By calibrating it with a baseline, it is able to detect changes in Earth's gravitational field that correspond to the motion of groundwater. And we were unable to find a way of compensating for this at this time. Additionally, atmospheric distortion is an additional source of uncertainty to our land surface temperature measurements. While we correct for this while computing the artificial surface index through normalization, we can't do the same thing with the land surface temperature, since normalizing it would, of course, ruin the land surface temperature values. We're getting it's in degrees Celsius. You can't normalize that. We thus conclude that there does not appear to be a significant correlation between groundwater quantity and the strength of the urban heat island effect in a city, but more research is definitely needed to confirm these findings. Thank you. And here you can see some of our references. Additionally, we would like to give a big thank you to Dr. Yitong, Dr. Oluwafemi, and Dr. Czajkowski for their assistance throughout the program. Additionally, we thank the NASA Seas Initiative for the wonderful opportunity to learn more about satellite data. Thank you, and we will now open the floor up for questions.